Welcome to lesson 9.1 part 2 and your flipped classroom. Now, the last and final example in this lesson has to do with rationalizing the denominator. If you remember what we learned earlier today, we learned that there cannot be a radical in the denominator. So what do we do when we're looking at a problem and that's exactly what has happened? The radical in the denominator does not simplify. It's not a perfect square or a perfect cube. How do we get rid of a radical in the denominator? So there's two different ways. It depends on whether your denominator is a monomial or a binomial. So let's talk about a monomial first. If the denominator is a monomial, you are going to simplify the numerator and denominator if possible. That's always going to be our first thought. Can I simplify these radicals? When we realize that we can't, that brings us to step number 2. We have to multiply the given fraction by a new fraction. Well, where are we going to get this new fraction? The new fraction, and I want you to take your highlighter and I want you to highlight right here, the new fraction is going to be the given denominator over itself. It's going to be the given denominator over itself. So really, you could add a note right here that says the radical over itself. The radical over itself. Because that is what is going to be in the denominator. It's going to be a radical and we need to get rid of it. Lastly, you're going to go back to elementary multiplying. You're going to multiply the numerators and you're going to multiply the denominators. Now, what if the denominator is a binomial? You look at the problem. Once again, you're going to simplify the numerator and denominator if possible. But let's say you've simplified all you can and there is still a radical in the denominator. You're going to multiply the given fraction by a new fraction. Exactly what we just did. But here's where it gets a little bit complicated. The new fraction is the conjugate over itself. So I want you to fill in the blanks, highlight. Now that's great. It's the conjugate over itself. But you got to know what a conjugate is. So a conjugate is the same binomial that you see in the denominator, but a different sign in the middle. So the same binomial with a different sign in the middle. That is the conjugate. So highlight, fill in any blanks that I left. And then the last thing that you're going to do is you're going to multiply the denominator and you're going to FOIL the denominator. Multiply the numerator, FOIL the denominator. Now you'll notice if you look really closely at FOIL, I crossed out the O and the I. So really when we FOIL the denominator, we're only going to have to multiply the first terms and the last terms. And we'll look at why here in just a minute. So example number 3, it says simplify the expression. If you look at letter A, we have 1 divided by the square root of 5. And of course, we're first looking at the radical and asking, can we simplify it? Well, 5 is a prime number, so we're not going to be able to simplify that radical. So at this point, we look at our rules. We're supposed to, step 2, multiply the given fraction by a new fraction. Now, is this a monomial or is this a binomial? Well, I can tell very easily and quickly, and hopefully you can too. This is one term. This is a monomial. So the new fraction, because we're supposed to multiply the problem by a new fraction. The new fraction, we're going to go ahead and put our multiplication dot, and we're going to go ahead and put our fraction bar. The new fraction is the given denominator over itself. So that monomial of the square root of 5 is going to go over itself. Now, I simply multiply the numerators. 1 times the square root of 5 is the square root of 5. And do you remember the shortcut that we talked about at the end of today's lesson? We talked about what happens when you multiply a radical by itself. If I do the square root of 5 times the square root of 5, I get the square root of 25. Well, what's the square root of 25? The square root of 25 is 5. So the shortcut that we're going to use, we're going to remember and understand that when we multiply a radical times itself, we ultimately get the number under the radical. So the square root of 5 times the square root of 5 is just 5. And now our problem is in its simplest form. You say, Ms. Johnson, there is a radical in the numerator, but that's okay. The only place a radical cannot be in our final answer is the denominator. Look at letter B. We have the square root of 10 divided by the square root of 3. Again, we're looking to see if either of those radicals will simplify. We know 3 won't because it's a prime number. 10, if we did upside down division, would be 2 times 5. There are no pairs to pull out. So there's nothing that we can do to simplify these radicals. So we're going to write our new fraction and we're going to be multiplying by that new fraction. Now remember, the new fraction is the given denominator over itself. So the square root of 3 over the square root of 3. Now, remember what we also learned earlier today. We are allowed to multiply numbers as long as they are both underneath radicals. So 10 times 3 can be done because both of these numbers are under the radical. So we have the square root of 30 divided by. Now, here we are, the square root of 3 times the square root of 3. The shortcut says a radical times itself gives us the number under the radical. So we have a 3 as our new denominator. Now, before we box this in, we have to make sure that the radical is in its simplest form. We have a new radical, so let's take 30 over to the side and let's do upside down division. 2 goes into 3 once with 1 left over. 2 goes into 10 5 times. 3 goes into 15 5 times. Now, I've got no pairs, which means the square root of 30 cannot be simplified, and this is my final answer. Now, letter C. Hopefully you noticed right off the bat there is a fraction under the radical, and we learned earlier today that we were going to separate the numerator and the denominator before we do anything else. So the square root of 2y squared divided by the square root of 3. Now let's see if anything simplifies. The square root of 2 will not simplify because 2 is a prime number. So I'm keeping the square root of 2. However, the square root of y squared, that's a perfect square. So the square root of y squared is y, and y goes outside the radical. Now the square root of 3, again, a prime number, so it cannot be simplified. And that brings us to a point where we would like to box this in, but we see that there is a radical in the denominator. So we're going to multiply by a new fraction, and once again, the given denominator is a square root of 3. So we're going to make the new fraction the square root of 3 over the square root of 3. Now, we can't do anything without y, so we're just going to bring it down. But the square root of 2 times the square root of 3, again, because both numbers are under the radical, we can multiply them. So 2 times 3 is 6. And here we are again. The square root of 3 times itself just gives us the 3 underneath. And we cannot simplify the fraction y over 3, so this is our final answer. Now, that's what you do when there is a monomial in your denominator. But what do you do when there is a binomial in your denominator? We still have to get rid of the radical. So if you look at letter D, you'll notice there's a square root of 3, and we look to see if we can simplify it, and we can't because 3 is prime. So we have to multiply by a new fraction. So let's go ahead and put our multiplication dot and our fraction bar. The question though is, what is the new fraction this time? Because this is a binomial, the new fraction is our conjugate over itself. Now remember, the conjugate is the same binomial that we see in the denominator, but with a different sign in the middle. So we're looking at 1 minus the square root of 3, and we're going to put that over itself. Now be very careful because this 8 is a monomial, and you are dividing it over here by a binomial. So whatever you have to do to remind yourself, this is going to be the distributive property. So you can put the binomial in parentheses, or you can simply draw an arrow from 8 to 1 and from 8 to the square root of 3. But you have to remember to distribute the 8. So 8 times 1 is 8 minus, now I cannot put 8 and the square root of 3 together. I can't multiply them because one of them is outside of a radical and one of them is under a radical. So imagine that that square root of 3 was an x. We talked about how radicals and variables have a lot of the same properties. Okay, so 8 times the square root of 3, since we're not able to actually multiply those numbers together, we're just going to write them down beside each other. 8 times the square root of 3. Now, remember what we said about the denominators. We are supposed to be foiling them, but we crossed out the O and the I. Why did I cross out the O and the I? What is the special product that allows me to multiply with a shortcut? Well, today in class we did the square of a binomial. This is the other special product that we've learned. If you look at these two binomials, this one and this one, what is the only difference between those two binomials? Hopefully you're saying the signs are different. Everything matches but the sign. So this is the difference of squares. And I want you to write this in your notes. Difference of squares. Over here beside, we're going to draw an arrow, but we're showing ourselves that this is the difference of squares. So we multiply the first terms, 1 times 1, and we get 1. And we multiply the last terms. the square root of 3 times the negative square root of 3. So we already know a positive times a negative is a negative. And again, the shortcut, the square root of 3 times itself gives me the number under the radical, which is 3. So I have 8 minus 8 times the square root of 3 divided by negative 2, because 1 minus 3 is negative 2. Now, this is where it gets just a little bit tricky, because remember, fractions must be simplified. Fractions must be simplified. So here's what I have to make sure I understand. There is a binomial in the numerator, and the only way that I can simplify is if all the pieces will reduce. So I have to imagine 8 divided by 2, which is 4. And then I have to imagine negative 8 divided by negative 2, which is positive 4. And of course, that square root of 3 does not go away. Now you're like, you lost me. Okay, imagine this. Imagine this was 8 divided by negative 2 and negative 8 times the square root of 3 divided by negative 2. Because that denominator of negative 2 goes with both parts or both terms in the binomial. So 8 divided by 2 is that negative 4, and negative 8 divided by negative 2 is that positive 4. So you can include that in your notes if you need to, but this is how we end up with negative 4 plus, oh, and wait 1 second. Remember, I want the radical term first, so we're going to switch it. 4 times the square root of 3 minus 4, and that will be my final answer. Now, look at letter E. Again, we check the radicals first. Can we simplify them? Well, 13 is a prime number, so it's not going to simplify, and also 5 is a prime number, so it's not going to multiply or simplify. So we have to multiply by a new fraction. Now, this is a binomial, which means the new fraction is the conjugate. Same binomial, different sign. So the square root of 5 plus 2 over the square root of 5 plus 2. Now again, be very careful. This is a monomial times a binomial. So put the parentheses or draw yourself the arrows. It does not matter to me, but show yourself the distributive property. Now, the square root of 13 times the square root of 5, we can actually multiply because those are both underneath the radical. So 13 times 5 is 65. Plus, again, I cannot multiply 13 and 2 because one is under a radical, one is outside the radical. So I just put them together, 2 times the square root of 13. Now remember, the denominator, everything should match but the signs, making this the difference of squares and making me able to FOIL without the O and the I. So if I multiply the first terms, I see that's my radical part this time. The square root of 5 times the square root of 5, a radical times itself gives me the number under the radical, and negative 2 times positive 2 is negative 4. So I have the square root of 65 plus 2 times the square root of 13 over a 1. Now, when we have a denominator of 1, we really can eliminate it. We don't need it. So I'm going to go ahead and take it off. But before we box this in, we must see if the new radicals will simplify. 13, prime number. It's not going to. 65, there's a good chance. So over to the side, let's do upside down division. 5 goes into 6 once with 1 left over. 5 goes into 15 3 times. 13's prime. There are no pairs. So the square root of 65 plus 2 times the square root of 13 is my final answer. And last but not least, letter F. Hopefully you're getting into the groove of this, all right? 2 cannot be simplified. The square root of 7 cannot be simplified. They're both prime numbers. So I'm multiplying by a new fraction because I cannot have a radical in the denominator. This is a binomial, so the conjugate, same binomial, different sign. So the square root of 2 minus the square root of 7 over the square root of 2 minus the square root of 7. And here we are again, a monomial times a binomial. So give yourself the reminder with either the arrows or you can put the binomial in parentheses, but you must distribute. So I can't multiply 12 and 2. One's outside the radical, one's under. So I'm just putting 12 times the square root of 2 minus, can't multiply the 12 and the 7. One's outside a radical, one's under. So again, 12 times the square root of 7. I notice the two binomials are the same except for the sign, so that is my shortcut again, reminding me I can FOIL without the O and the I. So the square root of 2 times the square root of 2, shortcut says a radical times itself is the number under the radical. And the square root of 7 times the negative square root of 7 is negative 7, because a radical times itself is the number under the radical. So I have 12 times the square root of 2 minus 12 times the square root of 7 over negative 5. Now remember, if I'm going to reduce this, every piece has to be reducible, if that's a word. So 12, negative 12, and negative 5. Is there a number that goes into all three of them? Because if there's not, the problem stays as it is, and I cannot reduce. I don't know of a number that goes into 12, 12, and 5, so this is my final boxed-in answers. And that is how you can rationalize the denominator. Get rid of the radical in the denominator before you box in a final answer. Guys, that is lesson 9.1, part 2. Have an awesome night. I'll see you tomorrow.